Today we will discuss the performance of operational amplifier for different frequencies. A response of operational amplifier for different frequencies. That is, to find out the characteristics of the operational amplifier towards AC. Operational amplifier is basically differential amplifier. It amplifies the different signal applied at the inputs. So differential input is VID, that is difference of V1 and V2. And input resistance is RI, output resistance. RI is the input resistance, and the output resistance is R0. Operational amplifier having very high input impedance and very low output impedance. Here is a voltage source, that is the voltage is amplified A times. So the voltage source becomes A times VIG. Now there is a capacitor. It is not attached externally, but the BJT and FET, they are used for making operational amplifier having some internal capacitance, that is the C. And here is the output voltage is V out. Now, ideally, op amplifier, is having infinite bandwidth. Ideally, op amplifier must having infinite bandwidth. Bandwidth mean the frequencies. Infinite mean all the frequencies ranging from 0 to infinity. Infinite bandwidth mean all frequencies gain of the op amplifier remain constant for all the frequencies ranging from 0 to infinity. But in real practice, it never happens like this. All frequencies here mean frequency from 0 to infinity. Now, in real practice, it never happens like this. In real practice, op amplifier gain decreases with increasing the frequency. Now there is a word, special word, that is called roll off. Roll off mean that the reduction of the gain of the operational amplifier with increasing the frequency is called the roll off. Now the question is, what is the reason of the roll off? Why the gain reduces of the op amplifier while with increasing frequency? That means, what is the reason of the roll off? This is the important question. So the answer lies in the fact that op amplifier made up from bipolar junction transistors and field effect transistors, and they are having their internal junction capacitance. And these capacitance having the reactance 1/C omega. As the omega increases, the reactance decreases. And because this capacitor, it is in parallel with the output voltage. So sub signal, a part of the signal becomes grounded, with the reason that the output decreases with increasing the frequency, and hence A becomes a function of the frequency. This is the capacitor for which the gain of the operational amplifier becomes a function of the frequency. This capacitor is not attached externally, but it has the reason of that because operational amplifier is made up of transistors and FET. They are having the internal capacitance, junction capacitance. So that's why the capacitor play a role for decreasing the gain of the operational amplifier. Now let us calculate the V out. So this is a closed loop, and in a closed loop there is a voltage source AVID. So how we find the current? Current equals to the voltage source, which is A into VIT. The voltage source is A into VIT divided by the total resistance of the circuit. Total resistance is R naught plus resistance of the capacitor, that is 1 over JC omega. So this is the current flowing in a loop. Now this current is responsible for a voltage drop at the capacitor, and V naught across the capacitor, which is also the output voltage, it becomes the current into 1 over JC omega. Now substituting the value of the I here in the expression, then V naught becomes equals to, after substituting the value of I, V naught becomes equals to A into VID divided by R naught plus 1 over JC omega multiplied by 1 over JC omega. Now we to simplify this expression and taking the LCM on the right hand side of the denominator, that this becomes R naught JC omega plus 1, and then this not plus sign here, it is a multiplied sign, actually it is a mistake. So divided by again JC omega, then this is a multiply sign and this is now corrected, 1 over JC omega. Now JC omega and JC omega gets cancels out, and output voltage becomes equals to, V naught equals to A into VID upon 1 plus R naught JC omega. Now keeping in mind that the omega is 2 pi f, now we are interested here finding V naught over VID. That becomes equals to A over 1 plus R naught JC omega. Now the A V naught over VID is a gain, which is a function of the frequency. Now because omega is 2 pi f, substituting this omega in the expression, then V naught over VID becomes equals to, this is V over VID, it is A gain, which is a function of frequency. It is A divided by 1 plus R naught J C omega mean 2 pi f. So this is the gain, which is a function of the frequency. Now we have to substitute, we consider a factor. So let we consider factor, which is let me call what that 1 over R naught 1 over 2 pi okay R naught C as not F naught, actually it is a mistake. We are calling 1 over 2 pi R naught C is F naught. Now 2 pi R naught C becomes equals to 1 upon F naught. So here this is R naught is there, and 2 pi is there, C is there, 2 pi is there, and C is also there. Substituting here 1 over F naught. So this is a term which is we substitute it here in the expression 1 over F naught here. Then AF becomes equals to A upon 1 plus F upon F J F upon F naught. So this is the expression of the gain of the operational amplifier, which becomes a function of the frequency. So we are making the correction that the let factor is not F but F naught. So it is again 1 over F naught. Now this is a function. This is a gain of the operational amplifier, which is a function of the frequency, where F naught, which we fixed in the expression, it is 1 over 2 pi R naught C. R naught is the R naught and C, they are the internal factor of the operational amplifier, and that means F naught remain constant for a given operational amplifier. The F naught is constant for a given operational amplifier. Now the gain which we are getting, which is a function of frequency, it is equals to A upon 1 plus J F upon F naught. This function implies that with increasing F, A decreases, because F it is in denominator, and with increasing F, A decreases. So this AF means gain of the operational amplifier, which is a function of the frequency. And on the other side, on the right hand side expression, the A which is in the numerator, it is also the gain. A is also the gain of the operational amplifier, but this is without any frequency, mean when DC is applied, or you can say when the frequency is equals to 0, then the gain of the operational amplifier is A. And F is now a function of frequency, because F it is in denominator. So now if we take F equals to 0, now what happens? AF becomes equals to A. That means there is no difference between AF and A at when the frequency equals to 0. Now F naught is given a name, and it is called break frequency, and it is constant for a given operational amplifier. F naught is called a break frequency, or it is also called the cut-off. It is also called the cut-off frequency. It is also called the cut-off frequency of the operational amplifier. This is also very important, because in the graph we will study that how the gain decreases from while increasing the frequency from 0 to F naught. Now this AEF having the two parts, because there is it is coming J in the denominator. It is having two parts, the magnitude part and second the phase angle. Magnitude part and the phase angle. So we to study separately the magnitude and the phase angle. That means how the magnitude it varies with increasing the frequency. Second, how the phase angle it varies with the frequency. So first of all, we take the magnitude of AF, and how we get the magnitude of AF? Very simple, that it is equals to A divided by the root of 1 plus f upon f naught whole square. This is the magnitude, and magnitude it is clearly that with increasing f, the magnitude of AF decreases. On the other side, how we find the phase angle? AF, phase angle of the output, which is a function of the frequency. Is it in match with the input, or is there any the phase difference between input and the output? So if we make a triangle of the base equals to 1 unit, if we make a triangle of the base equals to the 1 unit and perpendicular equals to f upon f naught, then the hypotenuse, this is a phase angle which is phi, and the hypotenuse becomes the root of 1 plus f upon f naught whole square. Now from this triangle, we find the value of the tangent phi. Tan phi is perpendicular over base. Tan phi is perpendicular divided by the base. Perpendicular is what? F upon f naught, and base is 1. So tangent phi is equals to f upon f naught. From here we find the value of the phi, and phi becomes the tan inverse of f upon f naught. Tan inverse of f upon f naught. Actually what happens, the phase actually it lags behind. So if it is lagging behind, we put a negative sign also. So phi becomes equals to the minus of the tan inverse of f upon f naught. Now that we are having the expression of phi, we are having the expression of the magnitude of the gain, which is a function of the frequency. Now we will see how the variation of the both with respect to the frequency. So for IC 741, let f naught equals to 5 Hz. For this integrated circuits 741, f naught is 5 Hz. And the gain, open loop gain is very, very high, like 2 with 5 zeros. For operational amplifier, open loop gain is very, very high. Now for this data, for these values, constant values, A and F naught, let's try to find the gain at the different frequencies, magnitude of the gain with the different frequencies in decibel. In decibels, and in decibels the formula is 20 log to the base 10, and then A upon 1 root of 1 plus f upon f naught whole square. And this is the formula of the gain in decibel. So we make some columns like frequency f, then gain AF in decibel, and we know very well the formula that 20 log to the base 10 and A upon root of 1 plus bracket f upon f naught whole square, and then we find the phase angle. It is equals to minus, which is a function of frequency, minus tangent tan inverse of f upon f naught. Now what we do, we take the different frequencies starting from 0. First of all, if frequency is equals to the 0 Hz, and then substituting here f equals to 0, f equals to 0, what happens? that becomes 20 log 10 A, because the denominator becomes 1, and then substituting A, the value becomes 106.02 decibel, and phase becomes 0 degree. So what we did, we substituted the 0 value here in the formula. So at 0 frequency, the gain is 106.02 decibel and phase angle equals to 0. Now we substitute, we take the frequency 5 Hz, then slightly gain comes down, it is 103.01 decibel, and there is a large change in the phase, it is minus 45 degrees Celsius. Sorry, minus 45 degree, not Celsius. It is minus 45 degree. Now we take another value of the frequency, keeping in mind 5 Hz was that frequency, which is called the break frequency. It was also the 5 Hz. Now we take the value of 10 Hz. With 10 Hz, slightly more gain comes down. It is 99.03 decibel. Whereas again, the phase changes with a large value, minus 45 to minus 63 degree. So this is again a large change in the phase. So if we take frequency 10 times more than previous, meaning if we take the 100 Hz frequency, it is 10 times of 10. Then what happens to gain? It comes down 79.98. It comes down by 20 decibel. This is very important when the frequency increases 10 times, gain comes down by 20 decibel, and then there is again increase in the phase with negative sign, it is 7.13. Minus 8, phase increasing in negative, and the change in the gain is 20 decibel. Now we take frequency again 10 times still more, like we take the frequency 1000 Hz, 10 times more. Then again it is very important, gain time comes down by again 20 decibel. It becomes 60 now, with increase in frequency 10 times. Gain comes down by 20 decibel, whereas the phase angle, which was increasing in negative value, now it is minus 89.71. So now the change in the phase is decreasing. Now we're making the frequency 1 with 5 zeros. This is not 10 times. Okay, now the gain comes down to 20 decibel and the phase angle becomes minus. There's a very small change in the phase, minus 89.99, not much change in the phase. Now we're making frequency 10 raised to power 6. We're making 10 to power 6, the gain becomes 0 decibel. That is very, very important. At this frequency, the gain becomes 0. And there's a very small change in the phase angle, minus 89.999. So this is very important. The gain is changing with the very small values when the frequency increasing to the very large values, like 1 with 5 zeros and 1 with 6 zeros. And this change in gain is much, So this is the variation of the gain with the frequency and variation of the phase angle with the frequency. Both are very, very important for plotting the graph of AF versus F and phase angle versus F. So if we took graph of magnitude of AF, which is the value shown here, and the f, the value shown here, and the phase angle, the values are shown here. If we plot the graphs, and the graphs between AF and F, between phase angle and F, the graph is like this. Very, very important. The F frequency is increasing along the x-axis, and the value of the gain, it is highest at 0 degree, coming down, and at the break frequency it is minus 3 dB down. At F naught the gain is minus 3 dB down. Then gain decreases linearly, down in gain, and here at this frequency the gain becomes 0. This is F dash frequency. Let we call this frequencies as F dash, where the gain becomes 0 decibel. Whereas now look about the phase. Now phase at frequency 0 was 0, and phase decreases very rapidly initially. Initially it is decreases very rapidly. Not it decreases, you say. It is increasing in negative value. Okay, and at F naught it becomes minus 45 degree. Now further increasing, there is a very, very small change, but the phase angle never touches to minus 90 degree. It never touches to minus 90 degree. It remains close to 90, okay, at the high frequencies. So frequency increasing 100, 1K, 10K, 100K, 1M, and then the phase is a small change. So this type of the variation of the magnitude of AF versus F, and phase angle versus F, all keeping in mind that break frequencies was F naught was also 5 Hz. At 5 Hz the gain is decreasing by 3 decibel, and this is another frequency of the break frequency. Break frequency is that frequency where the gain comes down by minus 3 decibel. Okay, so it is called minus 3 dB down. So this frequency also called corner frequency. This is another name of the F naught. The break frequency is also called the corner frequency. So this frequency where the gain becomes 0, let we call it F dash. Now we try to find the value of the F dash. How we find F dash? F dash is where the magnitude of the gain in decibel becomes 0, and in magnitude its value becomes 1, because then log of 120 log to the base 10 into 1, that is 0. So the magnitude of AF, so magnitude of AF with log it is equals to 0. It is equals to 0, and but the magnitude part like AF, it is equals to value equals to 1. Now we find the value of F dash by substituting the value of the magnitude of AF. Now what is AF? AF we know very well. AF in magnitude, it is A upon 1 plus F upon F, not F, F dash over F naught over whole square. Now it is equals to 1. Now just solving this expression. Now 1 is negligible because F dash is very, very high. So it is negligible. Then root of F dash over F naught square, it just left F dash over F naught. So it becomes A, then it is F naught upon F dash, it is equals to 1. Now from here we find the value of F dash. F dash is equals to A into F naught. So F dash is that frequency where the gain in decimal reduces to 0 called unit gain frequency. Mean it is that frequency where the magnitude of the gain becomes equals to 1. So this is the unit gain frequency, and f dash is equals to a into f naught. Unit gain frequency, this is called f dash, where the gain in decibel becomes 0 and gain in magnitude where becomes equals to 1, unit gain frequency. It is that frequency. Now we're writing the definition here. It is that frequency where the gain in decibel becomes 0, gain in decibel becomes 0, and the gain in magnitude, it is 1. So gain in decibel becomes 0, and in magnitude it is becomes 1. That frequency is called, f dash is called the corner frequency. So it is also where f dash is called unit gain frequency. This is very, very important. The unit gain frequency, f dash is called, you know what unit is called? This unit frequency, the another name is also crossover frequency. This is also called the crossover frequency. So this crossover frequency or unit gain frequency formula is A into F naught. A is the, unit gain frequency is equals to A. This is open loop gain when the frequency is equals to 0. Okay, when no AC is applied. When no AC is applied or 0 hertz, multiplied by break frequency, which is F naught. Okay. So this is very important formula.